Hello. This is still a presentation on the review for exam for chapters 6, 7, 8, and 9. This on the board has more to do with chapters 8 and 9. The previous video was about chapter 6 and 7. And again, we want to think about them as a logical progression in the sense it is all about population to parameter, about inferential statistics, whereas chapter 7 we didn't know the parameter. In chapter 8 and 9 we do know the parameter. And in chapter 7 the estimate that we got was what we considered to be a good, efficient estimate of the population parameter, and we enclosed it in a confidence interval to give us a little more confidence, which you saw and you've seen in the book and you saw in that video. Here again is chapter 7, where we've got 95 out of 100. Anything that falls within that, and this is our mean. This is the sampling distribution again. I didn't mark it all or identify all the features of it, so that anything that lands within here, 95 out of 100 probability of the true parameter being there, even though we think that our mean is a valid one because of all the things we did with the central limit theorem and all of that. So, but when we get to chapter 8, we've got basically the same kind of diagram, whereas in chapter 7 we wanted to land inside, shall we say, because everything inside is similar and everything outside is dissimilar. In chapter 8 and 9, we don't want to land where everything is similar. We want to land in the tails where things are dissimilar. Now let's talk about this for a second. The other way of thinking about this normal curve is not just a frequency curve or a percentage curve or a proportion curve, but a probability curve. Anything that's happening under the heap of the bell has a high frequency. I mean, there's a lot of X's under here in that histogram, if you can imagine the bars, vertical bars of the histogram. There is a lot going on there, so that means that things in that heap are very similar to one another. As you move away from the mean, going to the right or the left, the frequencies decline in number, and hence they become less frequent or less probable of occurring. So this is a probability distribution. High probability, 95 out of 100. Low probability, split the 5 into 2.5 over here and 2.5 over there. So you want to keep that in mind as a probability distribution. The closer you get to the tail, the less probable something is of occurring. When you get to chapters 8 and 9, that probability, low probability of something occurring is we like in statistics, because then we can say if our sample value falls in one of these rejection zones, then we can say it has a low probability of occurring. Consequently, it's not likely to have happened by chance. So we can, with some comfort, say that we can statistically say that the difference between the population parameter and the sample value are statistically significant. We have a model 5-step process for chapters 8 and 9, an algorithm, if you will. If you follow that and you do the put in the appropriate formula in step 4, you'll get the answer for what you need for the decision in 5. So let's think about this for a second. Here we know the parameter is known. Let's step back, and one of the illustrations in chapter 8, and it'll work for both 9 and 8, is let's say that we're interested in a neighborhood of the city of elders where, because of some subjective work we've done in qualitative methods, focus groups, key informant interviews, whatever it might be, we suspect that the crime rate against the elders in that neighborhood is much higher than what is known to be the crime rate against elders overall in the county, because we can get that from the police department, right, for the county. And so what we want to do is we want to help those elders come up with a crime education program that will lower the frequency of crime in the neighborhood. So what we want to do in that case then is we want to find out what the crime rate is in that neighborhood, and then look at that crime rate and compare it to the population parameter crime rate, and be able to say, using a hypothesis testing, that it is statistically significantly different. If we can show the evidence of a statistically significant difference, then we can go before the county judge or whoever the funding source is and request, say, $250,000 to develop a crime education program with the elderly. So here we're trying to show something dissimilar. Now let me speak for a moment about this. This is the null, your sample value, the rate in your neighborhood the null would say it's equivalent, more or less, to the population parameter of the county. So we set the P here in the center of this probability distribution so that, let's say that this is 10, and our value out here is 20 out here. And so what we're saying then is that we think that it is higher than in the neighborhood than here, and we want to test for that difference. And what we're hoping is that this value will be out here in this tail on the right-hand side, because it's larger than this one, would be out here, and so we could show that it is statistically significantly different. Now, we have to back up for a moment, because if you're out there in the world, you have to get the S, you have to get the sample value. In order to get the sample value, you may have to go back to Chapter 6, think about that whole process, drawing down a sample of elders. You can't ask every elder in the neighborhood because there's too many, cost prohibitive. So you call down a sample of the elders, draw down a sample of the elders, and then do the statistic to get the rate for that sample. And then once you have that sample, you can close it in confidence intervals if you like. And because at that point you'd be estimating not the parameter of the population of the county, but the parameter of the elder population of the neighborhood. So when you did that sample value, you're estimating your neighborhood population parameter of crime. So then you take that sample value and you put it over here in Chapter 8 to show that the value of that sample that you derive for your particular neighborhood is statistically significant than the larger one, the one for the larger county as a whole. Your research hypothesis says they're similar. Your null, your research says, and what I advocate for you, and you can see this in the chapter, is unless for some reason you're instructed otherwise, always do a one-tailed test. If you see that your value in your population, in this example is sample rather, is 20, and for the overall county is 10, you can see this is larger than that. So then you would take a one-tailed test and say that your sample value is larger than your population value. So unless you're instructed otherwise, for whatever reason, do a one-sample test, because the two values of the parameter and your sample are in front of you. Don't be wishy-washy. It's a competitive environment out there, and when you're going for funding, stick your chest out, speak boldly, and show the evidence of how you see this as being statistically significantly different. Okay, now, when we're doing this in terms of the sample size, there are a couple of procedures you have to choose from. If your sample size is less than 100, you're going to use a t-distribution, whether it's Chapter 8 or Chapter 9. If your sample size is larger than 100, you're going to use a z-distribution, whether the sample is, whether it's Chapter 8 or Chapter 9. Now, the difference between Chapter 8 and Chapter 9 is, in Chapter 9, it's a two-sample case. You'll pool the two estimates. Your two samples that you come down, let's say in Chapter 9 you want to look at the difference, if there's a difference in crime rates for males and females. So you pull down a sample where you can distinguish a sample of males and a sample of females. So you pool those two ends of those two samples in order to test the difference between those two samples. Are they in fact statistically significantly different? If they're statistically significantly different here, then you can conclude that they're statistically significantly different up here. Perhaps you decide that you don't want to focus on just generally elders, but you think that the women are more vulnerable to crime. So you're going to show in your process that women are more, statistically speaking, more vulnerable to crime, and you can estimate that that's true in the larger county population or in your population of your neighborhood, so that you can direct your funding towards crime education among the women and maybe not put so much focus on the men. Okay, now I think that, again here, let's just say for example, this is similar, similar, dissimilar, dissimilar. So let's say that, let's say for example, when you did this one about the crime here, you find that this, if we're doing a 95% one tail, and you can look at your textbook how that works, a one tail 95%, this would be a 1.65 z-score right here. And this would be your rejection zone. So that your z critical is 1.65. If you get a z observed in this case that is greater than 1.65, say it lands out here, you can reject the null. That's the consequence of your calculations of Chapter 4 will lead you to the decision of Chapter 5. If you find after you do this that your z observed is less than 1.65, maybe it lands in here somewhere inside the similarity zone, then you fail to reject the null. You may see a trivial difference in the amount or the value of your sample as opposed to the value of the parameter, but it's not statistically significant. I cannot emphasize enough for you to do that 5-step model. Look at your assumptions in step 1. Step 2, figure out what is your z distribution. As you're using a z distribution, your t distribution. Set your hypothesis rather in step 2 in the null in your research hypothesis, calling it a one-tail where you can. In step 3, you do your z distribution, your t distribution, and then step 4, you pick the appropriate formula, which may have to do with size of sample, or it may have to do whether you're dealing with a proportion from a categorical variable or a mean from a continuous variable. And then you do your calculations in 4, and what you'll find there is if your t is larger than your t critical, you reject. If your z is larger than your z critical, then you reject. If your t is smaller than your t critical, you fail to reject. If your z critical observed rather is t observed and t observed and z observed are smaller than your t critical or your z critical, then you fail to reject. Follow that 5-step model and you'll come out with basically the right idea every time. So that Chapter 8 and 9. Now Chapter 9, you have those pooled estimates. There's 2 ways that you can do a 2-sample case. You can pull down one sample where you've taken care to say, let's you want to compare males and females of elders on crime, where you have a large enough sample for males and a large enough samples of females inside that, and then you can pool those 2 samples in a pooled estimate. The other way you could do it is you could do a double whammy sample and pull down one for guys and then one for gals. And why would you want to do the double process like that? Just do one sample, taking care that you have sufficient size samples inside that, one for males, one for females, and in a single sample, separate them out to 2 samples and follow the procedure of Chapter 9. Now, one other thing that's important to keep in mind with Chapter 9 is you want that sampling of males and females to independent. You wouldn't knock on the door of a house and a lady comes to the door and you say, what can you tell me about the crime rate? And then she tells you, and then you say, can I speak to your husband? No. What you'd want to do is say, thank you very much, and then go to another house and look for a guy to answer the question. You have to assume that 2 people, a husband and wife, or significant others living in the same house, will have had enough kind of conversation that they may agree on the crime rate. So you may be getting a couple's response rather than an individual's response. So in order to keep it clean in that sense, you would go to, if that lady answered, then the next one would be you'd search out a male. The other thing I would suggest if you're doing this kind of sampling is you wouldn't go next door, because maybe they know one another and they're having conversations with tacos in the afternoon and coming up to some agreement about crime rate. You might want to, if you're doing a sample like that, get a female on one block, go to the next block, get a guy, go to the next block, get a guy, go to the next block, get a female. Keep them somewhat geographically separate so you don't have to worry about independence and dependence. You've got some assurance of independence. Independent sampling is what I'm getting at. Okay, that's Chapters 8 and 9. And so I'm going to close this out. In a little while I'll send you both these videos, and we'll be posting this exam on Friday. Now, YouTube takes a while, not a long while, but I've got a community meeting this afternoon and they may not pop up for me until the afternoon, so you may not see these YouTube videos until tomorrow afternoon, which is Wednesday, which is still a day or 2 out from the actual exam. Give you some time to prepare. All right.